Oh, sorry. Yes.
Okay, I think we have everybody. So let me introduce our speaker today, Syed Naqvi, who came from us from Kraków. He's working at the moment at the Institute of Nuclear Physics, Political and Sciences in Kraków. He did his PhD also in Kraków at the Jagiellonian University, and currently he's working on basically exotic world objects. You were part of LIGO.
Yeah, last year I was
part of working with LIGO, and he's working on gravitational waves. So please, Syed, happy to have you here.
Thank you. And I should stop by 12:15 before. Sorry, people sleep probably before. Okay, so hi everyone. I should have color-coded my slides because it's absolutely right. Okay, so I'm Syed Naqvi. I'm a postdoc at IFJ Institute, and some of the slides would be particularly aimed for students. If it is too basic, apologize. But the idea is to at least spread this knowledge of gravitational waves and get some intuitive questions from you guys. So last night I was up awake and I was not able to sleep because I was scared of the talk. So I just was playing around with ChatGPT. So with ChatGPT, what I did was I just put an image of gravitational wave, and I said that animate it for fun because it was late at night, and what it did was it did a pretty good job. So the still image was there and it somehow animated. Obviously, it's a large language model. I really don't care what it did, but you see that when these two massive objects are coming and these kind of ripples are emitting, right? And in this talk, the idea or what I would want to convey is two things. You see that these two guys are moving in not a circular orbit, but it's an eccentric orbit. So that's one. And you see that these objects are not actually spherical. So let's say if Earth is spinning, we know that because of the spin, it gets oblate, right? So because of the spin of the object, the object is deformed, and when these objects move around, they emit a gravitational wave signal, which is, let's say, quite different. So this is the untrue picture, but by the time I reach to conclusion, and if you are awake, we will see what the true picture is, like the proper numerical relativity simulations. So the content is, first I will go through Einstein's journey to the famous quadrupole formula, where we try to relate these ripples in space-time in terms of the quadrupole radiation which general relativity has. Then the idea would be to peek into something which is called, obviously, gravitational waves. The idea is to look into different templates, because there might be different configurations. Like if spin are aligned, the gravitational wave signal is different. If spin are anti-aligned, it's a precessing signal. So the morphology of signals are different, and depending on your detector, and more specifically detector noise, then you do your parameter estimation, which is mainly you do it by Bayesian analysis. I will also present some results on Fisher analysis, which is let's say, a toy model study, but nonetheless important. Then the idea would be to at least convince you guys that this spin-induced quadrupole moment, according to general theory of relativity, is defined uniquely for a black hole. Because for black hole, you have only two guys, right? So you have mass and spin. And so if you have these multiple moments, what you see is that this value of kappa is 1. But for neutron stars and ECOs, exotic compact objects, this value of kappa is actually different. It's not 1. It could be different for a boson star, for a Gravas stars, or so on and so forth. And then finally, I will talk about this signal, GW241011. So when I was part of LIGO collaboration last year, we were doing some analysis on this event. And particularly the thing is there's two things, that it has an unequal mass ratio. And the thing is that the spins are very precisely measured. So it enabled us to do this study of exotic compact objects. So maybe I'll try to do this. And the next slide is from my outreach. So I apologize, it's not that great. So these are because you have to begin somewhere, right? So you have the Einstein field equations. Obviously, if the equations are complicated, you just know that there is something on the left-hand side and something on the right-hand side. And because I have forgotten what I translated in Polish, but let me remember, it was by, I think, Steven Weinberg, right? Oh, so space-time tells matter how to bend, matter tells space-time how to curve, that kind of logic. But obviously, why I use the Spider-Man meme is because there is a kind of non-linearity, which is very unique to, let's say, general relativity. And once you have the Einstein field equations, you can have different solutions of the Einstein field equations. And because I have been in Poland for 5 years, I fell in love with pierogies. So how I try to tell this is like, so you know how to make a pierogi, right? You have the dough and everything. So consider this as the differential geometry which you work on. But the stuffing which you keep inside the pierogi, let's say if you have pierogi Ruski, this would be a different space-time. Let's say space-time of, let's say, around the Earth or around a specific object. But let's say if you are into my favorite pierogi, which is pierogi the spinachium, then maybe these are space-times, or let's say exact solutions of Einstein field equations with gravitational waves. But in my PhD, I was working on very exotic space-time. So I thought that maybe later at life, there would be an Indiski pierogi. So these are space-times having standing gravitational wave nature. But these are completely not astrophysics. So today we will focus on pierogi the spinachium, which means gravitational waves, which you have a particular well-defined template for. And the gravitational wave, let's say, journey was very interesting. From doubt, it actually started when Henry Poincaré said that maybe accelerating masses might produce gravitational waves. So this was his notion there. And then in 1915 and 1916, Einstein linearized gravity. But still, as a full nonlinear theory, there were these issues in gravitational waves. So the plane gravitational waves in full theory, this was not known at that time. Then do full Einstein equations have a solution which can be interpreted as gravitational waves? Then do gravitational waves carry energy? And then the metric which Einstein and actually Rosen used to define gravitational waves has, it was an exact solution, but it had singularities. So there were these issues going on. And then it was the work by Bondi, Pirani, and Robinson that they were actually able to define plane waves in full theory. They did that. They found out that gravitational waves are a class of like well-defined solutions in Einstein field equations, and that they carry energy in form of a sandwich wave, which affects the test particle. And the missing puzzle was actually solved by Andre Trotman, who passed away recently. Because the radiation as a concept is non-local. And to define it in general relativity, you need boundary condition. And when Andre Trotman, kind of defined this, then is how the green light for, let's say, gravitational wave research was given. Kip Thorne came, you worked on astrophysical situations, so on and so forth. But finally, this was the journey from doubt to belief. So just a very quick reminder of what gravitational waves are. So you have these ripples of space-time, and what you tentatively do is that you have some massive object which is moving very far from the Earth. So on the Earth, let's say right now over here, I have the flat space-time, eta, AB, the guys with the X, Y, Z and time, but now combined because you are in general relativity. So you have space-time continuum. And what you do is you treat these gravitational waves as perturbations to the flat space. And that is what you are solving. And once you try to see what is the effect of these ripples in the flat space-time, you see the two polarization behavior. And if you're a student and if you are confused by this, don't worry. I shamelessly took a page from Hartle's book. And this is a rough analogy which you do in your electromagnetism, let's say. So you have, when you do electromagnetic theory, you have the scalar potentials, phi and A, the scalar vector and the scalar and vector potentials. That is your H alpha beta. In GR, you have linearized Riemann curvature, which is associated with, let's say, roughly analogously wise to electric and magnetic fields. And by the end, obviously, you know that in order to arrive at Maxwell's equations, you need some gauge conditions. So here you have Lorentz condition, and actually this is Lorentz, not Lorentz. These are two different guys. And then you finally have the D'Alembertian equation, right? A wave equation. A wave equation will have wave solution, and that's how you, let's say, theoretically motivate this. But right now, we were solving these equations when the right-hand side is 0. But you have to solve it when the right-hand side guy is there. And then when you include the matter term over here, what you see is that, and you have to do a bit of mathematics when you go from here to here, what you get is that your perturbation, those ripples, H, are related to the double time derivative of the quadrupole moment. It's actually reduced quadrupole moment, but this is not something very unique. If you remember your mechanics class, this reduced quadrupole moment is actually related to your moment of inertia tensor, which is related to your mass density, right? So mass deformations are producing gravitational waves, let's say. But let's say not the problem, but the thing is, if you take the double time derivative, you see that there is this guy over here, g by c to the power 4. And when you take, let's say, gravitational wave luminosity, it comes g by c to the power 5, extremely small number. But if you have very compact objects, let's say black holes or neutron stars, which we now know exist, then these give you a significant ripple which you can actually measure in the Earth. And if you put the value, if you want to calculate that energy carried away by gravitational waves, the peak luminosity at a black hole merger is 10 to the power 50 watts. And I'm not an astronomer per se, but let's say in luminosity wise, there is no source which has this much high luminosity per se. Now, a gravitational wave waveform, you can either look at the, so let's say when a gravitational wave signal is being studied, there are actually three phases. One is the inspiral, so which is over here when the two objects are slowly moving around. You have some approximation. I will tell you what they are. Then the intermediate when they are coming close to each other. Now your approximations are about to break. And then when you have the merger part, then obviously you need numerical relativity thing. So you put your Einstein equations in the computer, you solve it. And then you get such kind of a chirp signal. So in the frequency domain, if you see, the signal goes like this. So if you have heard the sounds of the space-time, so it goes like woo kind of thing, that is over here. Just try to keep this in your mind, because for an eccentric signal, this actually changes a bit. So let's say if I'm calculating energy of emitted from a gravitational wave, so the circular binary, I will get this formula. The gravitational wave signal looks like this, fine. But let's say if the objects are eccentric, so they have some, they are not circular, they have some eccentricity involved, right? Only this factor comes in, Fe. But you see that the gravitational wave signal has quite distinctly been different. People don't search for it right now, but this is important. Keep in mind. And let's say one of the first indirect gravitational wave detections which was done was the Hulse-Taylor binary pulsar, PSR 1930. So this was discovered in 1974. So you know pulsar is a rapidly rotating neutron star, and you get these light signals, right? So when they come towards the Earth, you see the blip. And these are, let's say, one of the most accurate clocks which you can have. Now, the orbital period was 7.75 hours. So they are coming close to each other, but Newtonian gravity can't explain this. You would need general relativity theory. So what people did is they did observations along the years of how this orbit kind of shrinks. So the blue curve is the theory, and the red are actually your data points. So this is actually very intense. And one thing important is, like, if you look at the length scale of the problem, so the distance between these two pulsars is around 10 to the power 11. The gravitational waves are emitted like this. So the wavelength is much larger than this element. Why this is important? Because the quadrupole formula which I showed you works under this approximation. Otherwise, it's not valid. So one has to work, let's say, two other higher methods. So this Hulse-Taylor binary pulsar, if you include eccentric, so let's say if you are observing the data and you observe a circular model, you will get the data points. But if you are including eccentricity, so it's actually an eccentric orbit, you see that the time to coalescence will shorten by a factor of this eccentricity. So eccentricity was there, but obviously that was not the main idea. The main idea was that if two bodies are coming close to each other, they are losing energy via gravitational waves coming together. And you see that obviously the data points are actually lying on your theory. So this was the first indirect detection of gravitational waves. And then it was good. And then obviously the gravitational wave, people were working on different gravitational wave detectors. So the current data reading detectors are the advanced LIGO, and I forgot to put Kagra over here. But here is what I wanted to show: the past detectors, which is, let's say, the advanced LIGO, versus the future detectors, let's say the Einstein telescope and Cosmic Explorer. And one thing you notice is, let's say, this is the sensitivity versus the frequency. So what you see is that as compared to advanced LIGO, Cosmic Explorer and Einstein telescope are a bit deeper. It actually means that they are observing a frequency which is, let's say, from very less to something which is like very big, which actually translates it to now you have to mitigate the noise and so on, but now you are more prone to the signal. So what happens is that the improved reach versus the 2G detectors, the advanced LIGO, the Virgo detectors, for the 3G ones, is that the SNR would be 10 times more, right? Because you are exploring more. You have so you can imagine as a bucket, right? The more water it fills, you have more signals to analyze. Here, the bucket is more widened, let's say. So that's why the SNR is good. The redshift horizon is around 20, and the detection rate would be quite high. So our group's goal, and I'm in David's group, and the idea is to study neutron stars oscillations of compact stars, because now once you have shifted from, let's say, this frequency at which a signal enters LIGO to over here, there are other signals also. So you need to be careful of what template you are using, and it's like a needle in a haystack problem, which I will come. So detecting gravitational waves is, the idea is that, okay, two objects are moving close to each other, and when they are moving, because they are losing the distance between them, they are emitting gravitational waves, right? That is what you are doing. And your job, our job, is to see how the theory relates to the data. Because so you will have a gravitational wave template which has an amplitude and phase, and you need to relate it to the shift in the mirrors, in the gravitational wave detection mirrors, right? So that's what I will try to let's say motivate on. So in order to know that, okay, this guy is a 30 solar mass black hole merging, how do I know it? I need to get the exact template. So in the in-spiral part, what is used is something which is called post-Newtonian theory, which I will go through right now. Then in the merger part, because the GR effects are so high, post-Newtonian theory actually breaks down. So you need numerical relativity. And then when the object is kind of settling down, so it's like a wine glass, right? If you clink it, it decays, the modes decay. And there you have to use your black hole perturbation theory. So people build waveforms in these three different domains, and they not exactly stitch it, but they make it come together. And then once a template matches your data, then you say that, okay, so and so was generated by a 30 solar mass black hole. I mean, so if a 30 solar mass black hole collides, the final would be a 55 solar mass black hole, right? Where did the 5 solar mass went away? It went away in gravitational wave radiation. So the issue is that you need a, let's say, correct template. And I probably won't go into post-Newtonian theory much, but here is like, you rewrite the Einstein equations in the flat space-time. So you remember that you have the famous Einstein equations. This is the one which we were dealing with. But now you have, because let's say when two objects are moving around each other, so you have the T mu, but they are emitting gravitational waves. Gravitational waves themselves have their own T mu. So this is the gravity gravitates kind of concept. So that linear part is also here. What you do is you expand the left-hand side, the H's, the ripples, and the stress energy momentum tensor in a parameter which is V by C. This V by C is very important because this is how the post-Newtonian the theory works. And then you plug back these equations and solve iteratively at each order. So initially you consider a point-point particle, but then point-point particle things will break because they are not point particles. So you would have to consider spin, you would have to consider tidal deformity. So and so effect, they enter into the post-Newtonian, the in-spiral part. And then the important part is you need to solve something. So near the source, the metric determines the equation of motion. So when you are, let's say two sources are here and I'm nearby, I need to study the metric. But when I'm far from the source, the equations of motions are determined by the radiated gravitational waves. And this is not doing justice to post-Newtonian theory because it took around 10 years or more research of, let's say, Luc Blanquet and Bala Iyer, who developed it. And why it is complicated, I won't go into detail. You can look over here. Is that when you are solving when you're solving a two-body problem, you have to match so whatever solution you get, let's say over here, the near zone where you are very nearby, you match it to the exterior zone, and that's how you compute these terms. But it is fairly complicated, and I will skip it with the help of me, that you have your far zone physics where you are saying that, okay, ripples are happening easily. But you remember that there are some multiple moments or some mathematics which you have done to match it to the wave zone, which you again have to match it to the near zone. And then obviously at the end you have singularity where post-Newtonian theory will break. You need numerical relativity over there. Now moving on to data analysis part. And this is what I was saying, that it is exactly this thing that your whatever gravitational wave template you have, it's like a needle in a haystack. And that's how you can incorporate other effects. But you need to be sure how closely they are with the physical reality. And most of the time, gravitational waves is something like this, that there is a noisy room and you want to listen to your friend. Like if there is a music party going on and you want to listen to what the other guy is saying. So typically, gravitational wave searches are divided into two things. One is modeled searches, and this is what I was a part of. So I was using this software called ICBC. This is what gravitational wave people use. And let's say if I have a gravitational wave signal with two objects which are anti-aligned. So what happens is that the orbital plane precesses, you see that the gravitational wave signal is quite different. But you already have a template for it. So you specifically look for signals of compact binary mergers, but with different effects. You have these different pipelines. And here you have a discrete bank of waveform templates. And then you try to get some posteriors that, okay, if I have anti-aligned spins, then let's say, what is my posterior on m chirp? Like, what is the posterior on mass? What is the posterior on spin? And then you have some confidence intervals where you want to stay. But on the other hand, you can have sources for which the templates are maybe, let's say, not known, or they are unmodeled sources, and that is also fairly important. These are the unmodeled searches. So they have, and I think there are pipelines, but one I know about is the CWB, which Marek quotes over here. So these search for and reconstruct gravitational wave transients without relying on a specific waveform. And this is very important, right? Because if you're looking for a template, then there might be a bias, right? I'm only looking for 30-30 solar mass, which might not be the case. So here you identify coherent excess power, and this is one of the pipelines which people use. So different pipelines get these triggers, and then they try to quantify that, okay, you know, such is a signal with so and so false alarm rate. False alarm rate means that if in 10,000 years, this is generated by an actual signal or a noise. So these kind of statistics people try to do. So in gravitational wave data analysis, which I have done till now, I have focused on the model searches, which use something which is called match filtering. So what you have over here is, let's say you have a gravitational wave template. It's big only for the animation. Actually, it's very small. So all you have in the detector data is noise. And what happens is that you match the template. Let's say it happens here, and you calculate signal to noise ratio, and you see that this guy keeps over. So you get a signal to noise ratio of that. So what you have is you are cross correlating the detector data using the noise weighted inner product to get something which is called the signal to noise ratio. But here also you have to be careful that you are using a template band. So it covers a grid of masses, spins, and orientations, but you have to scan over the template. So there might be a particular resolution till which you can get. What I mean to say is that I can differentiate between a 5.5 solar mass black hole merger, but maybe I will not be able to say between 5.5, 5.5. Why? Because that is not covered by a grid. I'm just giving a heuristic example. Because the noise is, and one of the things in your detector, because I don't know if you know about gravitational detector, essentially like this, right? So gravitational wave is coming here. There are these mirrors. These mirrors have, let's say, the noise part of it is a separate presentation in itself. And you want to analyze like how when the light goes up over here. So let's say gravitational wave is coming here, it stretches and squeezes. So the light going up and going here and here will be out of phase. But you have to be very sure of what is causing that. Anything can cause that. Let's say that thing. So you have to be very sure. And what people do is you need a ranking statistics or a likelihood. And how people try to answer this thing that if you have only noise, and I should have been careful because the h which is there, okay, the delta L by L, the distance you are measuring is 10 to the power minus 21 or something. It is the size of maybe a proton or something. So you need to be very sure what it is. So basically, what people do in, let's say, parameter estimation roughly is they are trying to answer this question, that what is the probability that the observed strain, the stretching and squeezing, was produced by an astrophysical signal rather than a noise. And one of the two things which people do, which I have known till now and have been associated with, is one is the Bayesian analysis, which is more comprehensive, it is reliable for realistic data. The other is Fisher analysis, which I will show the results for. These are like quick and approximate, but these are, let's say, not the final answer. So in Bayesian analysis, what you have is that given the data, you are inferring the parameters. So you have these posterior plots, right? And what you try to see is you try to get this guy called likelihood. It measures how well the data fits the parameter. So given a prior means given the information which you already know before. So this encodes our knowledge about the parameters. You have some evidence, and you want to find this guy, this e to the power s by h. And I should be careful. This is the one over here. So I have to be, this is h by h, which is coming here. The one. So this is how your theory relates to the data, that part. The other thing which people do is, let's say if you are working in Einstein telescope, right? You don't have the detector data, then how will you know that the detector is, let's say, working in those kind of situations? Fisher analysis, what it does is that it takes the information of your waveform sensitivity divided by the detector noise. This is the different for Einstein telescope, different for advanced LIGO. And then you try to find these covariances, or let's say these 1 sigma error bounds on your parameter. So let's say there is some parameter kappa s. This is what I will work on. So let's say you have this parameter space where you have chirp time, chirp phase, time of coalescence, phase of coalescence, m chirp, symmetric mass ratio, spins, the spin-induced quadrupole moment, which I will introduce, and eccentricity. And then you would want to find what are the 1 sigma errors. Given advanced LIGO and given Einstein telescope, what would be the thing? I know that Einstein telescope starts at a lower frequency. So it may be that it will give better errors or less errors on eccentricity. But for advanced LIGO, I know by the time the signal hits the detector, eccentricity is gone. So you will get worse errors there. That's the rough idea over here. Now moving on to my work, like why gravitational waves are, and like why am I studying eccentricity and spin-induced quadrupole moment? Here the notion is that there are actually, when you observe, when you observe the clusters in the universe, then you have these, let's say, two theoretical models that either they are formed, let's say the binaries are isolated, that they just merge and then they give you the gravitational wave signal. So these shed their, so even if they had some eccentricity at the beginning of time, they will shed it by the time they enter your detector. Right? This is the isolated binary evolution. But you can also have globular clusters where, let's say, two objects have eccentricity. They are almost about to circle, right? But there might be a third interaction that might help the binary retain its eccentricity. So in dynamically formed binaries, so this was the work done by Romero, Shaw, and Mappelli, eccentricity might be there when it hits your detector. And now the question is whether your detector is sensitive to eccentricity or not. So these are the issues, not issues. This is the case for eccentricity. And now the case for eccentricity in post-Newtonian theory, and this is what I was trying to say. So if you look at the gravitational wave signal for an eccentric binary, it's quite different, and this is time domain. But if you look at the frequency domain, this is something very interesting. Because if the circular signal was there, it could be just like this. But here you have these kind of harmonics. So it might happen that if you can utilize these properly, it may help you break some degeneracies in your waveform template. This is how people try to study it. So, and actually people, and yeah, one more thing is like eccentricity is it's not a higher order effect. It is the effect as it is. So what I need to say is like, if you have an eccentric waveform, it is circular waveform plus the eccentric effect. So this is not arriving at a higher V by C. So I should have put the post-Newtonian part before. So let me explain this. So the post-Newtonian expansion you do by the power of V by C, right? So V by C to the power square, V by C to the power 4. So all the effects, the spin-spin effects, whatever comes at each order, but eccentricity affects them all equally. It's not coming at a particular order. So that's why it is important. And this was the work done by Fawata et al., that if you ignore eccentricity, then you can get biases in the chirp mass or the symmetric mass ratio, even for like these eccentricity for LIGO sources. So these were people were trying to look at eccentricity. Now it is becoming more important because for Einstein telescope and cosmic explorer, you are exploring the lower frequency of a gravitational wave, where if you are using a circular template to do your data analysis, you will get a bias in your chirp mass. Why? Because the signal might be eccentric and you are using a circular template. So your chirp mass will be off. You will be doing a biased data analysis in one way. Now comes the important bit, the case for spin-induced quadrupole movement. So what happens is that when an object is, so let's say there are two objects which are spinning and they are emitting gravitational waves, fine. But if they are spinning and if you include the effect of the spin, the object gets kind of, it gets kind of deformed here, like this. So what happens is that the spinning motion of companion A, it creates a distortion in its mass distribution, which creates a distortion in the gravitational field outside the star, which is measured by the quadrupole. So remember that when two systems are moving around each other, you have a quadrupole radiation, fine. But if you include the spin of the object itself, it gets deformed. That adds an extra contribution to this quadrupole moment. That is what being added. And this quadrupole moment is associated with this spin-induced quadrupole moment kappa. And this would be the important guy for this curve, let's say. And what happens is that, according to general relativity, this value of kappa is uniquely defined, one for a black hole, but let's say for a neutron star or for an exotic compact object, you don't know the equation of state. So let's say if that guy is spinning, will it oblate in one direction or in other direction? These things are not uniquely defined. So those guys can have kappa different than one. Especially, let's say for neutron stars, the value of kappa is between 2 to 10. For boson stars, it is between 10 to 100. So these are fairly different. And now my motivation would be to at least help you understand how these guys enter the post-Newtonian wave. And this is the part where probably you will sleep, but let me try not to make you sleep. So you have the gravitational waveform, you have the amplitude and the phase, right? So this is what I was saying. So you have first post-Newtonian order. This is the V by C to the power actually 2. And once you go to the higher order, 1.5, spin effects start to enter. So you have the spin effect, which is the so now because the angular momentum will get coupled with the spin of the object. So that spin orbit effect starts to enter at 1.5. Now, if you consider the spin-induced quadrupole moment, you see that enters at 2 p.m. So this is where this guy, this QA, this spin-induced quadrupole moment, this kappa, this is where it enters. So it enters at 2 p.m., 3 p.m., 3.5, and so on. And this becomes important, and this was actually being studied because let's say this was studied for quasi-circular cases. So if you want to probe the mass gap between massive neutron stars and lightest black holes, these studies actually are important. And also if you want to study the existence of black hole mimickers, so let's say there is a compact object which collides with it. I don't see the electromagnetic counterpart. How will I know that is a compact object or a black hole, right? Because I don't see the electromagnetic counterpart, right? But if you have the measurements on, so let's say the signal comes, right? You can have the posteriors on kappa that can indicate whether it's a black hole or some other object. Then, and this was the work done by Krishnendu et al. That they did the Fisher analysis, and then Divijoti et al. They did the Bayesian parameter estimation because spin-induced quadrupole movement also arises at spin precession, so on and so forth. And my work, which I was doing last year, was just study this for eccentric cases. So that was the waveform which I had. So this is the waveform which was developed by Omkar, Soham, and Kaushik. This is in Chandrakant Mishra's book. So what they have done is you have the circular waveform, spinning circular waveform. So the information of kappa is here. This is one. But now the important part is you have eccentric corrections. So how the development of post-Newtonian theory went is that Moore et al., they added eccentric terms to spinning circular part. That is one. What these guys have done is they have added spinning eccentric terms to the spinning circular terms. So the information of kappa or the spin-induced quadrupole moment is now coming from both these parts. And this actually makes the waveform a bit more complicated. And what they have done is they have expanded this waveform in eccentricity to the power going to 8. Why E0 power to the 8? Because if a very highly eccentric binary is there of 0.5 initial eccentricity, then you would need E0 power 8 corrections. I'm not showing the waveform here because it's stupid. And what we try to do is we define this symmetric and antisymmetric combination kappa s of kappa 1, kappa 2, and then we try to find 1 sigma errors. And that is what I did in this conference proceedings paper, is that we've tried to find the delta kappa errors as a function of the total mass. So for, let's say, one thing to see over here is this is the advanced LIGO errors. So you see that advanced LIGO errors for delta kappa are above 1. So pretty much, let's say that. But let's say if you have Cosmic Explorer, the errors are much better. Why? Because it grabs the lower, let's say, let's put it this way. So the in-spiral part of the signal, the more I can get it, the more information I have. Cosmic Explorer starts at a lower frequency. I am gaining more in-spiral information, so I have better errors. That's what you see the development happening over here. And this is for E08 correction. So I have taken the full waveform. What happens is that at the lower masses, so when the masses are lower, these have large post-Newtonian cycles. So when the total mass of the system is small, they have higher post-Newtonian cycles into the detector. So which means that you have additional phase information leading to smaller errors. But if you look at this end of the plot, which is actually over here, you see that the errors are almost merging. Why? Because for heavy massive systems, by the time they enter the detector, they have shed their eccentricity. So eccentricity, according to this study, doesn't play a role there. So this was the analysis which we have done. And now the idea would be to continue it for a population of eccentric binaries, so on and so forth. But now I will switch gear and move to one more thing. This is what I was saying, that obviously that was Fisher analysis, toy model study. But let's say the people in LIGO collaboration, what they do is they use this kappa s. So this is the symmetric combination, and they write it as 1 plus delta kappa s. So if I have 5 gravitational wave signals, I measure the value of delta kappa. If the delta kappa is almost towards 0, which is over here, it means that the object has symmetric spin-induced quadrupole moment 1, which means that it is most obviously a black hole. So this is how people were trying to study it for different gravitational wave signals. So this was, let's say, the GWTC3 catalog. Maybe there were like 100 signals by then. Right now I think we have more than 300 signals now. But this is an earlier study, and this is like the full study where you do proper Bayesian analysis and you try to find the posteriors on the kappa. Now switching gears to these two guys. So this paper came in very recently. So GW 24 10 11 and 24 11 10. I get confused between 10 11, but anyways. So these are important in two aspects. One, that you see that the primary, so the primary is denoted by the one which happens in larger mass is 20, and the secondary is very small. So this is one thing. The other thing is that the spin is very high. Like the spin measurements in gravitational wave detections till now were not very confident, but here it was. And one more thing which I will not go into the detail is, if people want to study that, how does a 20 solar mass black hole come? So you can do some Bayesian hierarchical analysis, and people can more or less confirmly say that these were the parents of these guys. But one thing important I saw, and this was a very good infographic which I found, that this signal was 700 million light years away. And by that time, what we were doing, we were not existing. But these black holes collided when the Earth was covered in a blanket of ice. So this was like a pretty dated vaccine. Now, when you look at GW241110, here what happens is that the spin is high and it is anti-aligned. Similar thing, that the primary is very massive than the secondary, symmetric mass ratio, also possible hierarchical merger, and this was almost 2.4 billion light years away. We were still not there. When these black holes collided, Earth was going through a phase where oxygen started accumulating in the atmosphere. So these are like coming from way behind, say back in time. But our motivation, and yeah, why these two signals are important is because of this. So if you look at, so on the y-axis, you have the measurements on the spin. So of all the gravitational wave catalog, GWTC4 is the gravitational wave fourth catalog, you see that the error bars are very high on the spins. These two objects, for 241110, it is fine, but for this also, GW241011, this is the one which I will be talking about, you see that the error bars are extremely small. So the spins are measured very precisely. And what this actually does, it gives you, let's say, a window to test to test fundamental physics. And this is what people did. They again tried to see how, like, whether this object was formed from a black hole, so on and so forth. So this was the black hole spin-induced quadrupole moment. They found that the delta kappa is peaking towards 0. So this object is most likely a black hole. This was the conclusion of that thing. What we did, and actually what Krishnan et al. Did, and I was a small part of this. And yeah, one more thing. Here, when you are doing parameter estimation, you are using this kind of waveform. So remember, if I have the full waveform, I need the in-spiral merger ring down. So this is the in-spiral merger ring down phenom waveform, which has precession and higher mode. So this is like the full waveform which people use. And now what we did in our paper, in this paper, so implications of GW 241011 for rotating compact objects, is that Krishnendu et al., she is the lead author here. So she considered the posterior of this guy, which you already have. And then the question was that, given this event, what does it imply for a rotating compact object? Now, what does is that you have your kappa measurements, and now you try to map them on the exotic compact objects morphology. And I will try to go through what exotic compact objects are. There is a zoo of them, and let me take you step by step. So this is the diagram of exotic compact objects, which I learned recently. So let me go through. So at the center, so there are two axes. One is the reflectivity, right? So what fraction of incoming radiation bounces back, and the other is, this guy is called closeness. So I mean, this epsilon is called how close the surface is to the horizon. But it would be better if you think it towards the, I mean, you think it in terms of compactness, how compact the object is. So let's say if I'm looking at large compactness over here and large absorption, then people have, like in the literature, there are these models called tight fuzzballs. So these are also exotic compact objects. But let's say if I have small compactness and large reflectivity, because let's say if I consider a boson star, it will have a surface. So then you will have a boson star over here. So these are the four categories in which let's say the exotic compact objects are defined in terms of how compact they are and how reflective they are. So obviously at the center you have the black hole, most compact, zero reflectivity, and then you have this axis. And this is the slide by Paolo Pani, so you can follow the work, like the really good paper. And what happens is, like here I'm trying to say the same thing. So you have black holes at the origin, which is over here. So all the exotic compact objects are deviation from the common. So if you have a Grava star, boson star, diffuse fuzzballs, these are just deviations from your curve graph. And how they can deviate is like they can have a surface around the horizon or by reflecting radiation, so on and so forth. But the important part is this. The spin-induced quadrupole moment, the kappa which we study, we only probe the compactness. So the spin-induced quadrupole moment is sensitive to how concentrated the mass is. So compactness is defined by mass divided by radius. And this parameter, this event, GW14, 10, 11, actually sets a threshold on this compactness. So now the idea is that you have a zoo of particles. You try to calculate what compactness a boson star versus a graviton star would be, whether it lies within this. If so, then it might be that object. So what they have tried to do in this paper is they are saying they only have the posteriors on the primary. So remember, there is the big guy, primary, secondary. Primary one is the in which the spin was measured very accurately. So they try to answer this question that whether that primary object is a black hole or something else, or does it lie in the realm of rotating exotic compact objects. So a compact exotic object with compactness greater than 0.24 can be a graviton star or a thinly walled solitonic star. So this is what they were trying to study. So not all, and within the boson stars also, within these, there's a whole zoo of them. So not all boson stars are equal. Whether a boson star survives depends entirely on its potential, and some are fully excluded and partial. And this is how I will almost try to end the talk here. But let's look at the first the kappa posteriors, like how they look like. So this is the work where I was involved in. So GW24 1011 is obviously an ideal ECO laboratory, highly spinning, very asymmetric mass ratio. What it does is that it has given very unique constraints. So remember, kappa 1 is the spin-induced quadrupole moment of the primary object. So you see that it is not exactly close to 1, but somewhere over here. So the idea is that what it could be. And then, because when a gravitational wave signal is coming close to each other, you can choose to end your simulation or whatever at a different cutoff. So let's say if the two objects are coming here, if I cut off my analysis over here, then I'm cutting it off at 300 Hertz. So you see the posteriors is kind of very weak. But as and when they are coming close to each other, you are probing the signal more and more. So you have more information about the kappa, the guy which you are looking for. And that is how you see that for 1024 Hertz, the posterior is very high. So their question was what it could be. So amongst the zoo of exotic compact objects, that was the idea. And I will only take 2 of those. So the implication of GW2410, I will only consider these 2 boson stars. You can, and one more thing, you can just scan this paper and have a look at it. So what people have done is like, not people, what our group did is, so you have a boson star, right? Boson star has, I have completely zero knowledge about boson star, but I understand that there would be a Lagrangian, there would be a potential. That potential will depend on some mass term and some repulsive potentials. And then you have a space-time, you solve it together with this potential. It's not an exact solution, so you have to numerically solve it. And then let's say for different coupling constants, you get your different stars. And this gray region is the shaded region, denotes the kappa spin measurement at 95% credible level, which essentially means that if whatever star I'm taking, if it lies within this, it is acceptable. So let's say if I study boson star, one of the category is repulsive stars, and you see that all of them are lying outside this bound. So the primary is not a boson star with a repulsive potential. But if you look at solitonic stars also have this self-interaction part over here. So this is the coupling. So you see that when the coupling is, let's say, where is pink? Yeah. So when the coupling is greater than 0.1, these stars are almost out. So these you cannot include. But let's say if the coupling is very small, 0.04 of these stars are 9. So maybe that primary was a boson star of solitonic nature. But still, this is only one of the studies in the paper. You can see that there are some exotic fluid stars which they did the simulation, and all of them fall over here. So saying what that primary is, that the only thing this paper concludes is that object or that primary object has a spin-induced moment which is measured very uniquely. But what exactly is it? It's still very difficult to say. The only thing is that if the compactness of whatever stars you have, whatever zoo of stars you have, should be greater than this, then only it will fall within that region. But there is a catch which I will tell. So almost about to conclude a bit earlier, but I will just say what I'm doing. So the spin-induced quadrupole moment study has been done for circular binaries. Yes, my work in my last position was to do it for eccentric cases. So now the idea is that I know that you see that the errors were improving at lower mass, right? So the idea is to go beyond single events and do some statistical constraint for many detections. Because let's say if at a toy model, I want to ask the following question. If there are 1,000 eccentric binaries, how well can I constrain the kappa parameter? But if there are eccentric binaries and if I use a circular template, I won't be able to do that. I need an eccentric waveform. So that's what we are doing. And also to see that how including eccentricity affects the parameter estimation. Because you remember that that frequency curve is like coming like this. So maybe it is giving some additional information. The other work which I was involved as the LIGO Virgo member last year was that we coded up the SIQM eccentric terms in only the in spiral waveform yet. And these terms are coded in Lalsoot. We plan to do some injection and recovery studies and then try to see whether this kappa S is degenerate or not. And there is one thing which I forgot over here. This waveform is only an in spiral one. There is also a waveform developed by Kaushik. It's called E sigma. It's an in spiral merger ring down waveform, including kappa effects, like in the full phases of the gravitational sigma. And then we would like to see like whether eccentricity broaden the kappa S posterior, so on and so forth. And for the implication of GW24, this is one thing which Krishnendu wrote in her paper, and I felt it was very good. That Heisenberg wrote that what we observe is not nature itself, but nature exposed to our method of questioning. See, the thing which I spoke about right now was spin-induced quadrupole movement. So instead of point particles, there are spinning objects which are moving close to each other, like revolving around each other. But as and when they come together, what happens is that, let's say this is the object, the gravitational field of this will also cause some tidal deformability on this. These induces additional movement. So these are something called tidal deformability. This has not been included. So that's why like you cannot for certain say that this primary is a boson star or whatever. It might constrain some models, but your model as enclosed when they are coming close to each other, the tidal deformability will play an important role. So that's probably also very important. And oh yeah, and as I said that I would show you the how actually the signals look, not like not the ChatGPT version. So these are the simulations of GWTC4 events, actual simulations. So you evolve space-time in a grid of many points, and what you see is that, I mean, they are coming close to each other. The blue represents like they are almost towards the in spiral. When they are almost coming close to each other, you will see a bright light, which signifies that they emit a higher signal, not a radio or power. And these are how they look like, not the ChatGPT image which we have. And yeah, so you see that the maximum signal is given out when they are almost merging. And because students are there, so I can share my stupid story. So what happened is that. Okay, this is a bit embarrassing, but students, I guess, share. So at the beginning of my PhD, I was working in exact solutions, and I'm a crazy football fan, and generally I have names of physicists written behind. So at that time, I knew about Andre Trotman, and I ordered a football jersey of Andre Trotman written behind. But that time I ordered wrong from Allegro. I ordered a JG size instead of a Mainsky, so it's a very tiny jersey. But I used to think that maybe if I found Andre Trotman, he would like to sign the jersey, but then he would be like, why is this random Indian dude trying to get a football jersey signed? By the end of my PhD, I finally ordered a Polish football jersey, but that time I was reading Marie Curie. So this jersey is with Marie Curie, and the jersey number is atomic number of an element, which probably you would know better. So that's it. I like.
Thank you very much, Syed, for really, really nice talk. Do we have any questions? So maybe I can start while people think. So you say, so if you have this reflectivity and compactness, I know that neutron star is not really exotic, but where does it stay? Where is it in that diagram?
So actually, good question. I don't know about this. The only thing I know is that the value of that kappa, so the value of this spin-induced quadrupole moment is between 2 to 10. That's so it would be before the boson stars and all. Why? Because boson star, the value of kappa is between 10 to 100. But then, as I'm reading this paper, it realized that you can consider a specific mass of a boson star, and you can get any mass you want. So that might overlap with the neutron star kappa. So that ways I actually don't know, but it would be somewhere before the boson star. I guess, but I may be wrong.
And what actually the mass ranges of these exotic objects that we are looking? Here's like you are considering LVK detections, which is like presumably black holes, but are they exotic compact objects that can be in the mass ranges of like 10 or 40 solar masses?
So that is what in this model what we consider is, so there are some Grava stars or there are some fuzz balls. They are motivated by string theory. There, because you can tweak the mass element, so they might come in the range of 10 to 40. So that's why this becomes important, that if I do not have an electromagnetic counterpart, and if I only have a gravitational wave signal, how will I know that that is a black hole between 10 to 40? I mean, you obviously, if your template matches, if your false alarm rate is fine, but then putting that constraint on the exotic compact object becomes a bit complicated. And that's what now the idea would be like, because you only calculated the spin-induced quadrupole moment, but that is one side of the picture. When this exotic object would be coming together, the tidal deformability will also play a role. So that will have, and let's say tidal deformability for a black hole is zero. But for exotic compact objects, it depends on the equation of state of whatever object you have. So maybe that might change the picture.
I see.
Yeah, just following this, what if there's halos, for instance, of dark matter around these objects?
So this is one of the study which I'm doing with my master's student, that if you have let's say if you have a neutron star, then people study this thing called dark matter admixed neutron star. So the dark matter can either be around the neutron star or at the center. What it does is, if I don't consider the rotating case, it's even for non-rotating case, it affects the tidal deformability parameter. And then currently what I'm trying to do with the student is getting that errors on this tidal deformability, depending on whatever equation of state. So I have a baryonic equation of state. I can add the dark matter part. I can see how it changes the lambda. I change that lambda value to the waveform e to the power I psi, and I try to get the errors. So it is, for now, the preliminary results shows that it is different. Yeah. But these are Fisher results, so they are not that concrete.
Maybe somebody online has a question. So maybe one more question. What will be the rate of finding these eccentric or exotic objects? Is like 1 per, say, 1,000 detections, or maybe like 110,000? Is there like some estimate?
So as far as I know, like the number of neutron stars detections which were done was like one in a year or something, but I actually don't know the number of detections kind of thing. But that would be a good thing to look at probably. Sure.
Okay, so thank you very much, Syed, for the talk. Yeah. Yes.